Yo. Let's do another rational graph. Example. This one you're going to want to listen to. Fx equals x squared minus 2x plus 4 over x minus 2. Okay, I'm going to speed this up here, so just hang on. Yeah, I am recording. If you remember from last time, finding a vertical asymptote, super easy. This one has a vertical asymptote at 2. Do you remember what has to happen for a horizontal asymptote? You check the powers. Now, if these were the same powers, you would divide the leading coefficients. If the power on the bottom, on the denominator, was larger, that would be a horizontal asymptote of 0. All right? We haven't dealt much with what happens when the numerator has a higher power.
No.
Okay, here's where you need to write. Probably need to write. If numerator has a larger power, there's no horizontal asymptote. However, you might not have gotten into this last year in pre-calculus. Maybe you did. If the numerator is larger by 1 degree, there is a slanted asymptote. So this graph is actually going to have a vertical asymptote, which represents a domain restriction, and then it's going to have a slanted asymptote, which still describes end behavior, just like a horizontal asymptote does. Okay?
Pardon the interruption. Can you send Tanner Johnson to the front office for a minute?
Yes.
But if it's, would the slope just be 1?
I'll show you here in a second how to find. That's a good question. Let's at least state what we know. I'm going to use VA for vertical asymptote. What is a vertical asymptote? X equals 2. We already know that. Okay. Here's how you find a slanted asymptote. You're going to love this. This brings back memories. Does this look familiar?
Oh, I loved doing this. I can't remember how, but I remember it was fun.
You find a slanted asymptote by doing the division.
Oh yeah, this was the.
Okay, and I'm going to assume we all remember this perfectly. So, right?
Yeah.
How often does x go into x squared? How many times?
2. Oh, X amount of time.
X amount of times. Because x times x is
2.
x squared, and then x times negative 2x, or x times negative 2 is negative 2x. Now you draw your line and
Change the sign.
change the signs. Is this ringing any bells?
Yeah.
Okay.
So fun.
These cancel. Those also happen to cancel.
None of
And we get a 4. You drop down the 4. What is this right here?
It's a remainder.
That's your remainder. So you add the remainder over the x minus 2. That's your quotient.
No, we're done.
Or the quotient is x, the remainder is 4 over x minus 2. This right here, you guys need to make sure you mark this clearly on your home or on your notes, so mark it clearly. This quotient right here, it doesn't really matter what the remainder is actually. Whatever the quotient is, that's the equation of the slanted asymptote. Not the remainder part, but just the quotient here. So in this case, we just had a quotient of x. We might have gotten something like x plus 2 or x minus 5 or 2x plus 3. Whatever the quotient is, that's the equation of slanted asymptote. So on your graph, yeah, because it has a slope of 1. So it's a line that has a slope of 1. Okay, you guys, on your graph, you're going to have a vertical asymptote at 2, like we already said. The slanted asymptote has this equation, y equals x, because x was our quotient. What is the graph of y equals x? It's a line going through 0, 0. So this is an asymptote right here.
Can you imagine for slanted asymptote with y equals x squared?
That one we don't get into.
Is that more advanced enough?
No, it's just, that would be a difference of 2 in the numerator over the denominator. To end up with x squared when you divide. Anyway, so we have a vertical asymptote, we have a slanted asymptote. Let's go back to the original problem now. X squared minus 2x plus, what was it? Plus 4 over something something over x minus 2. Let's go back and do some of the things from last time. Let's find the X-Intercept first. No, let's find the Y-Intercept. What's the Y-Intercept? You let all the x's equal 0, so these are all gone, all those x's there.
No, negative 2. Excuse me.
So it's 4 over negative 2, which is negative 2.
So we know this one's going to be like that.
Now, to find the X-Intercepts, if it's rational like this, and it's only one rational piece, all you got to do is set the numerator equal to 0. Yeah.
So we said there are instances when you cross a horizontal asymptote. Can you cross a slanted asymptote or no?
Usually not a slanted asymptote. Okay, does this factor?
Yeah.
Are you sure?
Not anymore, I'm not.
I was pretty sure.
Does anything multiply to 4 that adds to negative 2?
Yeah.
No.
Okay, and just to save time, you guys, just to save time, if it doesn't factor, your only option is to use quadratic formula. If you did, you would end up with non-real solutions. Non-real solutions means there's no X-intercepts.
So we're fine. We're just chill.
So we know it's going to be in that top little B.
No X-intercepts.
No.
Again, it's because this has no solutions that are real. It has complex solutions, but no real solutions.
How did they create solutions?
Okay. Now, what does that mean about where this graph has to fit?
Up in that little B right there.
Because there's one point here already, there has to be a graph, or there has to be a piece of the graph right there, because there's a Y-intercept down there. You guys following? Here's a critical thinking question for you. I don't want you to draw this just yet, but consider this. Why is this not an option?
That's a function.
It crosses the y-axis, and it shouldn't, and it wouldn't also be a function. Remember, it has to pass a vertical line test, so that's not going to work. What about over here? That wouldn't pass a vertical line test. Where's our only option for another piece to this graph?
Why wouldn't that? Oh, because it comes from. But why couldn't you do, like this?
Because it would cross the x-axis.
Oh,
And then you'll have a 0 there.
Thank you.
Okay. Now, you guys, just more than likely, this would be enough information to accurately choose a correct graph out of 4. Now, in the case that it's not, are you listening carefully? Let's say that there's 2 choices on the test that have the slanted asymptote in the right spot, the horizontal asymptote in the right spot, and this y-intercept. How do you choose correctly? You would find the first derivative of this to find the relative minimums and maximums. This right here would be a relative minimum. Over here would have a relative maximum. You could do that to get more information if needed. You guys understand what I'm saying?
Yeah.
If you needed to. I don't think you will, but if you did.
Just go until you don't.
Okay. Let's move on to a different type of graph. Radical.
Yes.
Shut up, dude. You know what's going on.
I love this stuff, Terry. Radical.
Radical. Okay, here we go. You guys with me?
Yeah, we're with you. Whoa.
It wasn't like, you didn't do it.
Dude, not really good.
There are similar problems dealing with radical. We have to figure out where vertical asymptotes might be. Because remember, you can't square root anything that's negative. And also, you can't have anything that's 0 on the denominator. So if we have anything that's negative, or if we're having 0 on the denominator, that would be a vertical asymptote, or that would be undefined values in the domain. Okay? So you got to think about this critically and use some logical reasoning. This expression right here, x squared plus 2, is that ever going to equal 0?
No.
Okay? Is that ever going to be negative?
No.
So now let me ask this question. What is the domain of this function?
All real numbers.
You guys understand? The only problems we would ever have is if we're taking the square root of a negative. Is this ever going to be negative? The only other problem we would ever have is if we had a 0 on the denominator. Is this ever going to equal 0? So there aren't any problems in the domain. So what's the domain? So because of that, is there a vertical asymptote?
No.
There's no vertical asymptote. Are there any holes in the graph?
No.
So this is a continuous function from negative infinity to positive infinity. So there's no vertical asymptotes. Right? Okay. Now we're going to kind of go out on a limb here when we're talking about horizontal asymptotes. Okay. This isn't really the case where you're going to want to compare degrees, since this isn't a polynomial type expression. It's the square root of x squared plus 2. Okay. So you listening carefully.
Yes.
A horizontal asymptote is only on a graph to describe end behavior as x approaches infinity, or as x approaches negative infinity. Would you guys agree?
Yes.
Look back at your notes for just a second.
Okay.
Not at the one we just finished, but I don't know, this one here, for example. This was from last time. This horizontal asymptote right here, do you see on the screen?
Mm-hmm.
Doesn't it describe the behavior of the graph as x approaches infinity and as x approaches negative infinity?
Yeah.
That's why a horizontal asymptote is there. Okay? So, if we considered this problem,
Where is Craig?
the limit as x approaches infinity, wouldn't that tell us where the horizontal asymptote is? You guys understanding what I'm asking?
Yeah.
If we're looking at the limit as x approaches infinity, that's the end behavior of this graph as x approaches infinity. That would let us know the end behavior or the horizontal asymptote. The problem is,
It's all coming together.
if we plug in an infinity for x here and an infinity for x there, don't we get infinity over infinity?
Yeah, we can do that.
Because that's 1.
That's just one.
No.
It is.
That was called the indeterminate form. We spoke about this a few weeks ago.
Like that. Infinity by infinity is one.
That's called the indeterminate form. So, this is just one of these tricks that you pick up, and it works for the most part.
We're going to multiply by the conjugate pair.
What if...
I saw where you were born, guys. It's lovely.
What have I done there?
Whoa.
Times it by
I don't know what you mean.
x squared
I'm honest.
plus 2.
Divided everything by x squared.
Uh,
Okay.
Whoa.
wait, you divided everything?
Oh, yeah.
by
Just divided x over x squared over x squared, 2 over x squared. Okay. If we had more time, and if you were graphing this by hand, it would probably make more sense to go in this into more detail. This is not something you're really going to be expected to do, because on this test and on the AP test as well, I've checked with the other AP teachers, graphing something like this can be multiple choice, and you're just choosing the correct graph out of 4. You wouldn't be graphing it by hand. Okay. What this essentially does is it cancels out some terms. Okay. And with some more manipulation, you'd be essentially left with the square root of 1 right here. And what's the square root of 1?
1.
plus
Plus
or
or minus 1.
plus or minus 1. Okay, so that's where the horizontal asymptotes are. Plus or minus 1.
Babe, you were right.
Oh my gosh, I was right. What was I right about?
Infinity's right by infinity.
Is 1. We weren't losing the whole time. Oh my gosh.
So you have a horizontal asymptote at 1 and negative 1. Okay?
I'm just trying to make us do steps to get it.
Now, let's do some things that we can do using just basic algebra. How would we find a Y-intercept? This we can do. This one's no problem at all. To find a Y-intercept, you let x equal 0. So this x is 0, that x is 0. So we get 0 divided by 2, which is 0.
0 by
0 divided by the square root of 2, which is 0. Now, I just want to be clear that we understand what a horizontal asymptote is here for. Is this ever going to be possible?
No.
Because what's the horizontal asymptote? What does it say?
End behavior.
It describes end behavior. So as x approaches infinity and as x approaches negative infinity, this graph either approaches 1 or negative 1. So that kind of behavior is not going to happen.
Oh,
Okay? So either, here's your two options. Either it looks like this,
or it looks like
or it's the opposite and it looks like that. Okay? Or it could look like, whoa, let me get it.
Ooh, that'd be cool.
Or it could look like this. Okay? Something like that. So how do we know?
Got to test some points.
Just plot a couple of points. Plot a 1, for example.
Okay.
That's not where 1 should be. 1 should be about right there. Okay, anyway.
You put 1 all the way over there.
What's the sign of 1 if you plug in a 1? 1 over
1 over
1 plus 2 is 3 squared. Anyway, that's positive, so it's up here somewhere. And what about with negative 1?
positive.
If you plug in a negative 1, you get...
Oh, it's negative.
It's negative. So negative 1 produces a negative value. Positive 1 produces a positive value.
So we know what's going on.
And we know it crosses through the origin right through here. So the graph has to look...
I'm going to graph this on my calculator.
I wonder if Mr. Huff really could make an equation and make a picture, though.
Okay. That's all you really should expect on the test regarding a radical type graph.
Just hodgepodge.
Yes, kind of it does, except x cubes technically do continue to increase up and up and up and up. They never approach a horizontal asymptote. But yeah, it does resemble a cube root graph. All right. We got to get through this. I'm sorry. Trig graphs. Trig graphs. It's more than what you saw last year in pre-calculus. These aren't normal trig graphs that just oscillate between 1 and negative 1 and 1 and negative 1.
These are like...
Oh, these ones that like start bigger and then they get smaller.
They could, yeah.
Like a...
I think they start smaller.
Like a sound
Yeah.
wave.
Like a bouncy
Which means you're going to probably have two slanted asymptotes.
Oh yeah, and a
Sometimes.
A slanted asymptote named Ray. So didn't we learn that concept?
Okay.
It's like a ball bouncer.
Yeah.
Maybe a better way.
Yeah. You guys, this right here, on a test, when you have 4 graphs to choose from, it would most likely be sufficient to know where the horizontal or the vertical asymptotes are. Because look at the denominator, 1 plus sine x.
Yeah.
If we can figure out where that equals 0, wouldn't that tell us where the vertical asymptotes are?
Mm-hmm.
Okay. So most likely there's only going to be one answer choice out of 4 that has the vertical asymptotes in the spots that they need to be, and that would tell you which answer is correct. Okay. Most likely. So when is this equal to 0? That's equal to 0 when sine x equals
-1.
-1. So then you do the inverse sine. So think unicircle, you guys. Unicircle, where on the unicircle do we have -1 as a y value?
there and there. So pi
Up here is positive.
3
Right?
pi.
Up here is positive. One down here.
3 pi half.
That's 3 pi
Wow,
halves.
you really did it.
Okay, but remember, there's an infinite number of these. There's not just one vertical asymptote at 3 pi halves.
Okay.
So make a graph here. 0. Let's put pi, 2 pi, 3 pi. I don't know why, but that's making me really hungry. Where would 3 pi halves fit into all of this? Come on now, between
2 pi.
Between pi and 2 pi, so place a horizontal or vertical asymptote. Where would another one, instead of going to the right, I'm kind of running out of room here. Let's move to the left. Where would there be another vertical asymptote? Remember, it's at 2 pi k intervals. That's a full revolution. So if you started at 3 pi or 3 pi halves, I'm talking about in this direction.
Yeah, negative pi.
Negative pi halves.
Jack, can you explain me? I'm a bit lost about what you did. You put in 1 in this K, or you put in...
Well, first of all, you put 0 in,
Yeah.
and that gives you this asymptote right here. And then if you wanted to travel to the right, you would use positive values of k. But if you want to go to the left, you do negative, so k could equal negative 1. That means negative 2 pi. So you're just moving left around the unit circle. Or for you guys, it would be left around the unit circle, which is negative pi halves and 3 pi halves are the same spot.
Yeah.
So that would be another vertical asymptote. Okay. So it may be that just knowing where the vertical asymptotes would be enough. Okay. But if there's 2 graphs that have vertical asymptotes in the right spot, you're going to have more information. What other information could we easily find out about this graph? Easily find out.
X-Intercept.
First thought that came to my mind were X-Intercepts. Isn't that where that equals 0?
Yeah. Which cosine?
You could
0?
find X-Intercepts by where that equals 0.
The cosine 0 is at pi halves and 3 pi halves.
Cosine of x equals 0
No need right there.
at
Pi halves and 3 pi halves. Alright.
let's see, where we have x equals 0, we have x equals 0 as a pi halves. But also we have one at, but what's the problem with that?
That's an asymptote.
That's an asymptote, so that's no good. So that one wouldn't be, that one wouldn't work because that's a domain restriction. So we know there's one at pi halves
Plus 2 pi
plus
k.
2 pi k. So anyway, we know there's going to be an x-intercept right there.
So every pi halves that you can get to without hitting an asymptote.
Mm-hmm.
That's a good point.
What else could we easily find? What if we let all the x's equal 0? What would we be finding in that case? A y-intercept. What's the cosine of 0? Cosine of 0 is the cosine of 0.
Whoa, sorry. Whoa.
You're bad.
Whoa.
Cosine of 0 is 1. What's the sine of 0? 1 plus 0?
1.
1 divided by 1?
1.
So we know that there's a y-intercept at 1. So we know that this portion looks like that. That would most likely be enough information to choose the correct graph. It resembles a tangent graph. Yeah. It's actually a cotangent graph. Tangent graphs are in this direction.
Cosine divided by sine.
Cosine divided by sine is
Oh my
cotangent.
god! Mr. Why I was gonna trick us like this.
No, it would be cosine of x plus cotangent.
So it wouldn't matter what you put in front of cosine or sine as long as cosine and sine from the top line, you would know just from that it's a cotangent kind of graph. Something with something changed on it.
Braden R. Sluffer.
Even if it's not even in the curriculum, I'll just sort of out of curiosity.
Braden
what
Dirty
changed
Sluffer.
something like that. Because yes, that's a
I saw him this morning too. He's a sluffer. And I'm letting him know when he watches this. Gabe, he's probably taking that.
That's a great question. I'll have to put some.
Oh yeah, Braden's probably taking the ASVAB, that dirty sluffer.
He probably is. Okay.
Found him.
That's